All right, good afternoon, everybody. I'm really glad you're here, and I'm really glad, especially if you came last week to our attempted discussion for Disrupt Math. I just want to start by acknowledging some of the ways in which I didn't do as well as I needed to do last week with that discussion. The session sort of centered Black voices and ongoing issues of violence against Black people, and I let it end up focusing too much on white voices and ideas and allyship, and also let us drift into the sort of more comfortable for white people diversity and inclusion conversation rather than staying really focused on the real issue that is violence against Black people. And so one way we can do a little bit better about that, I'm going to share a screen with some personal anecdotes on it. So since last week, a new hashtag has arisen in Twitter called Black in the Ivory. And so if one way you might learn more about the experiences of Black mathematicians and Black scholars in general is to read some of these. The first one, there's lots of amazing things here to learn from. I mean, horrifying, of course, but the first one that I picked here is from a sociologist who said that their dissertation, they had to change their dissertation committee because somebody asserted that that wasn't what sociology was. And I wanted to highlight this one because it reminds me a lot of the conversations we have in mathematics, that if it involves talking about identity at all, that it by definition isn't mathematics for some people, and that's a serious problem that is part of these issues. And so in addition to reading Black in the Ivory, I think people might, if you're looking for help on things to do to be better co-conspirators, for example, checking out the hashtag Strike for Black Lives, you can see all the things that people posted yesterday and today about what they did and what they're committed to doing. So that's another really important strategy for some of us to move forward. This seminar came out of a bunch of us feeling really isolated during COVID quarantine. And I love how it had produced a seminar that sort of is a broader understanding of a math colloquium. It's broader in terms of what participation in a colloquium mean. You're not just talked at. And a broader interpretation of what mathematics in this context means compared to some of the very narrow and problematic versions of a colloquium, where we can talk about things like we talked about last week, but those themes should be integrated across all of our work. But one of the things we need to do is we need to keep diversifying our perspective, because the five of us who run this are white. And so if this seminar is to continue past, say, this summer, then we need to keep growing. And so if you are at all interested in guiding whatever this thing is or becomes, please contact one of us, and we'll do something more formal as we get a little further in. But I just wanted to make sure that if you're interested in leading or guiding or being involved, please be in touch. All right, I'm gonna throw it to Stephen to get the rest of the session started.
Thank you, BK. And you know, you were talking about yourself and your own organization of that talk last week, and I think I speak for all the organizers when we echo those sentiments and appreciate the leadership that you took over that. And we all, I think, want to do better and do what we need to be doing. So thank you. All right. Well, today we have our main event, our regular event, I should say, coming up in a few minutes. But first, we are really excited for a special showcase. I'd like to introduce Selvi from the University of South Alabama. Go Jags. Selvi, you want to say hello?
Hi, everyone.
And also Padi Fuster from Tulane University. You want to say hello?
Hi, everybody.
Thank you, both of y'all, for being here. These folks are the co-directors of meetamathematician.com, which is a project to amplify voices of mathematicians from underrepresented groups by sharing their stories through interviews. So what we're going to do now is we're going to pause the recording a bit because we're about to show a video that they've produced, and you can watch that if you're watching the recording right now. Please go to their website, meetamathematician.com. We're just playing one of the videos off of their website, and then we'll come back to this recording. So thank you both for showing that. And again, if you're watching the recording, go to meetamathematician.com to watch some. There's lots of great videos on there. Why don't y'all tell us a little bit about this project?
Okay, well, thanks for inviting us and giving us a platform to introduce our work to this community of people. I'm Selvi, like Stephen introduced. I'm an assistant professor at University of South Alabama.
And I'm Padi from Tulane University. I'm a PhD student.
And we met at Tulane when I was a PhD student there. We're going to talk a little bit about Meet a Mathematician. So it's a collection of video interviews with mathematicians from underrepresented groups. And our mission is to introduce students to role models by sharing stories of mathematicians. And yeah.
So why did we started this project? So we are big fans of Latisms and mathematically gifted and Black. We love those websites, but we noticed a lack of like video interviews, and in particular short video interviews that give profiles of mathematicians. And we wanted to have a collective space for mathematicians of minorities.
And like we mentioned in our mission statement, we believe in the importance of introducing students to role models, because when you see people who look like you doing these jobs, like being like a math professor, then it feels more real, then you can be that person. So we want to do our part by sharing those stories.
And we believe in the power of personal stories. I think that they connect people so much more than like in any other way. And I think these videos connect a lot, both for the struggles that interviews talked about, and also for the inspirational words that they share. So it's both like kind of like the bad and the good, but through their personal stories, we hope that we connect people in much a more personal level.
Yeah. And by doing that, we also want to change this view of like how a mathematician looks like. When most of the people imagine a mathematician, the picture they visualize in their head is like one-dimensional. So we want to introduce these people to have more options. That picture does not represent most of us. So we want to change it by having these videos of mathematicians from different groups.
And yeah, and I think there's a lot of stereotypes on what a mathematician is, and it's not only the views, but also like, you know, like, oh, they need to be geniuses. And I think we have a lot of interviews with people that they may fail like their qualifying exam, or they were not always like good at math. And I think that that is very important for people to not push people away from mathematics.
Yeah, and we want to talk a little bit about what Meet a Mathematician means for us. So it's our baby. Padi and I met at Tulane when we were PhD students, and we're good friends, but besides that, I consider Padi as my action sister. So we keep each other on track to do things to like betterment of our community, like create awareness of the problems of people who are not like in the spotlight. So we started the AWM chapter at Tulane with our friends. Padi and I initiated it. And I am running a Grocery Code Club. I started Grocery Code Club at South Alabama. We have a Girls in Math Club at South Alabama. And Padi is doing...
Yeah, so I started this math conference that is called Math for All in New Orleans, which, yeah, I think it's like a great space, a safe space for people to discuss mathematics and for everybody to feel included in it, in the conversation.
Yeah, so the other thing, like why we're doing and what Meet a Mathematician means for us is we also want to change this view of, oh, if the math is the only thing you do, you can be successful. Like that should be the only thing. No, we want to change that story. We want to show like it is not the only way that will take you to be a successful mathematician. So in our interviews, for example, Michelle Manis, who is here now, she was one of the interviewees. Like it was not the only thing she did. She was interested in other things. Amy Radenskaya, she was a professional cellist for 10 years. Federico Ardila, he was, besides like doing his PhD, he was like playing soccer, he was like, DJing. So we are not one-dimensional people. We have a life and we want to celebrate that. Like we do things besides math that brings joy to our lives.
Yeah, so we're gonna share our website now with you for a second. I'm very happy that you all like mentioned, you know, like the climate that we are in now, and I think it's really great that finally people are taking action into changing, like, for better the world that we are in. And I think that we all are responsible, and we all need to take action into that. We just wanted to like share like a couple of organizations that they are fundraising, and one is the one that we mentioned, Mathematically Gifted and Black, which Candice Price is one of the people that started this, and they started this fund to support predoctoral mathematicians. And then the other one, the National Association of Mathematicians, NAM, which Ed Goins also one of, like, it's in one of the interviews, he's the president of this organization. And I think that you can become a member or donate. These are very like important things to do, but there's so many more things that needs to happen. Yeah.
Yeah. And I would like to tell you a little bit about how you can nominate mathematicians. So you see we have a collection of interviews with different people, and you can nominate mathematicians by filling out this form. So in this form, like you enter certain information, and there is this, oh, why is it not showing? Just a second. So at the end, there is this question, what makes this person a great interviewee? So we want to highlight people who are doing good work in terms of inclusion and representing their communities. But this is not only limited to people who are just doing inclusion work. So we also want to have a good representation of people from the math community. So please nominate people.
Right. So the last two little things that we wanted to share is like, how do we do these interviews? And so the reason why it's both Selvi and I presenting today, and not only one of us, is because that's how we do the interviews. It's both of us. We try to have a conversation with our interviewees. And I think like that makes like the conversation flow so much better. And we have like really amazing conversations. We're learning so much from these. We only record the answers of the specific questions that we make. And so for that, there is like a lot of editing that it requires a lot of time. We didn't know anything about editing before these, so it's a little bit of a struggle, but we're getting a little better, I think. Yeah, and then we always ask our speakers after we edit the interview if that is okay with them before publishing. So if that is something that is worrying you to not become an interviewee, don't worry, we always ask for consent.
Yeah, after we have the approval of our interviews, we publish these videos on YouTube and on our website, and we want to share a couple of ways you can use these videos. You can use them at math club meetings, like if your university math, like your undergrads have a math club or graduate students have a math club, they can use these videos. But also if you're doing outreach and have math club involvement for like younger students, you can use these videos. And you can share these videos with your colleagues. They are short, so it will be good to hear stories of other colleagues, right? And there are probably many more ways that beyond our imagination. So if you think of some, just let us know.
Yeah, and just finally, sorry.
Right.
Yeah, we just last sentence here. We just want to, like, if we show you our website, but we also have an Instagram if you want to follow us there. So you can share the interviews there too. And we also have a YouTube channel that you can subscribe. And if you can also subscribe to our mailing list from our website. And we always let people know when there's a new interview on. So yes, spread the word, please, because if not, this is not useful.
Yeah.
All right.
Thank you all.
Thank you guys. Let's give a hand real quick for that great showcase so far. I didn't see any questions in the chat. We do need to go ahead and move on. So I did notice on your website, there's an About Us link that has your emails on it. So folks can reach out to you and asking any questions that they would like. But I think at this point, we're going to go ahead and introduce our next speaker. Once I have my notes on, so I do it properly. Claire Merriman, why don't you say hello for us?
Hey, I should be in the process of getting screen share going, or maybe it's going. There we go.
There we go. Awesome. Thank you very much, Claire. Claire is a postdoc and director of the Buckeye AHA Math Moments Outreach Initiative at Ohio State. And she'll be talking with us about playing billiards to find continued fractions. Before we dive into that, let me just remind everyone how Talk Math with Your Friends runs. We like these talks to be interactive, and we want to have a discussion with an audience of friends rather than just have a lecture. If we have 40 people talking at the same time on Zoom, it'd be kind of hard to tell what's going on. So we have this format, we have this idea of a featured friend. And so do we have any volunteers of folks that would like to leave the mic off and maybe be a part of the active discussion?
Or mic on.
Mic on, excuse me. Yes, it's much more useful if you have the mic on. I'm sorry, did I say Ohio State University, not the Ohio State University earlier? I failed
Yeah.
that.
I think Noel volunteered.
So
So we have a geometer.
and so what we'll do is if you're not a featured friend, then go ahead and leave your mute on. Be muted. But talk in the chat. TJ is hanging out in the chat, and he'll have his mic unmuted so that he can have reply the corrections into the live discussion. So TJ just said hello in chat there. So is there anything else before we need to get started? Did I forget anything? Then let's go ahead. Oh, and then also hang around after the talk, and we'll have everyone will be with their be unmuted and have a nice discussion afterwards. So let's go ahead and get started, though. Claire, why don't you take it away?
Yeah. So thank you, everyone, and for coming and talking to us. So hopefully the title is giving you a little bit of an idea of where we're going and a lot of mystery. No idea why my iPad thinks it's 9:41 a.m. Okay. I'm in Columbus. I don't know. Those minutes are also wrong. But all right. Everything else seems to be working fine. So just as either a reminder or an introduction for a lot of you, if we were to play normal billiards, a square table is kind of the easiest thing to understand, right? If you actually go play pool somewhere, you're going to have a rectangle, but you also have friction and all of these annoying things in the real world. So our hypothetical billiard table here, the ball follows a straight line. There's no friction. There's nothing like that. It goes on forever. And the other thing we need to know is how it bounces. So when it hits a wall, we have this angle in, angle out rule. With light reflection, maybe that's a better analogy because there's no friction. So if we want to first start with this square, we're going to start with this question. So if it bounces around on a square and comes back to where it started, can we say anything about the slope of the path? It's a very open-ended question. So we'll let maybe the chat also think. I know
the
I've been
answer.
Here. What?
I think I know the answer.
Yeah, I was like, I think Noel actually knows the answer. Maybe featured friend is not the right person to say. Let's see if I can find where the chat ran away to. See if people had.
You're just getting lots of guesses for rational slope.
Yeah, so that is with all I've given you, that's all we can really say. I'll need pink in a second, but yeah, so right here, this is just going to be rational slope. With all we know, it comes back to where it started, and we have a square. So then the next thing is if I give you a specific one. So here we have a path. This is why I had pink. Now the question is, if I give you a path, can we say something a little bit more? So we know it's rational. Maybe those of you who aren't quite used to thinking about geometry, that's not as obvious, but there's a bunch of ways to get at that. But this is, I drew a nice one here, right? Like it bounces 6 times, comes back to where it started. This is a nice one. But we can have crazier things, so we want something that's like a little bit easier to understand. And so we start doing what's called unfolding. And we are going to use this here. The colors just kind of to keep track of the sides. So the first thing I've done is unfolded across this yellow. And so now instead of bouncing, we have that the particle goes just straight through the yellow. And then it's going to bounce off the red. And so these pink dots are just so I can connect the dots correctly. And then when it hits the black, we're going to say these two black are glued to each other. So we have kind of this torus thing going on. Or it's a cylinder, not a torus yet. Sorry, just spoiled the next slide. Right, so it goes out, and then we can unfold again across the red now. And so you do blue is glued to blue, and black is black. And now we have something that's kind of nice. So we could keep track, and this is by analogy, we will keep track eventually, of like how it hits internally. But in this example, everything is, the square is very nicely behaved. And there's a couple things we could do. We could keep doing this and unfold indefinitely and just get a grid on the Euclidean plane. Or we could say, you know, we basically know what's going on here, right? Like it's a square. What we can do is we can count how many times it hits the top. So let's see, we say this is start. We hit the side, come over here, hit the top, come down here, hit the side, and we go back to the start. And the slope ends up being the number of times it hits the top divided by the number it hits the side. I don't know if that's kind of at the bottom of the screen. So there is a way to get continued fractions here. This is not where we're going to do it because I kind of find it weirdly confusing. That's maybe the only time that someone declares the Euclidean case worse than the hyperbolic case. But plenty of people understand it. I just think that there's like a lot of matrices involved that are confusing.
Notability or something.
So what? Yeah, so the you can do it. But what I'm going to do is move into the hyperbolic plane. So, right, this is a lot of people coming from a lot of different types of areas of mathematics. So the upper half plane is the complex numbers with imaginary part positive. And then geodesics, which is our analogies are straight line, are semicircles centered on the real axis. They could have infinite radius, which is what you're seeing here. So they could actually be just vertical lines. And if we want to play billiards, we still have this rule of angle in equals angle out, but now you have to find tangents. So it's slightly more complicated than just doing the reciprocal of your slope, but it all still works. It's just more calculations. And we need a billiard table, right? Before we had a square. And this is where things start getting maybe non-standard to the geometers in the group who maybe have seen some continued fractions in the upper half plane stuff. Billiards is not normally what you're doing. So we are going to have this triangle. So believe me, this is a triangle. There's a vertex off at infinity. is our billiard table, and we're going to actually want some functions to understand what's going on. So reflecting across the yellow line, so reflecting across, this is the imaginary axis, is, we're going to call this A of z, which is minus z bar, which is, to those of you who are maybe used to seeing this, I saw the whole maybe I was like, wait, that's weird. Yeah, this is weird. We don't normally have complex conjugates, but what you want is this to truly be a reflection, and that is the function that reflects across the imaginary axis. It just means we have determinant -1. It's all phi for the geometers of the. It's not actually as scary as it looks. And then let's see, reflecting across 1 plus IR. So this blue line is, again, anything with reflection is going to have a complex conjugate. This is 1 minus z bar. And then across the red is e to the it, is c of z is 1 over z bar. So not used to thinking about this. This is hopefully not scary. It's probably actually only scary to people who've seen things like this before. Right, but we're gonna use the same idea. But there's a couple of things we probably need to be asking questions right now, like in the where is this going type thing, right? So before we found slope, right? So maybe an obvious question is, what is the analog of slope here? Right, like that doesn't necessarily make sense in this situation. Maybe people have thoughts. Maybe people don't.
Oh, Brian asked if a ball can return, which.
That is also
right?
a very good question. Yes, it can return to where it comes back. I will maybe at the end talk a little bit about how you figure out how to make that happen. Which is not purely geometry, I have to say, that like there's some algebra involved in the fact that what works actually works.
Oh, and also, do we end up with like a nice shape somehow here later? Because in Euclidean space, I'm like, oh, a square, and I feel really settled. And then in hyperbolic, I feel like that's going to get torn away from me.
Also good thought process. Yes, we do, and we will get into Mathematica pictures. I made this before I remembered that axes origin exists, and that I could, anyway, I made these pictures on the tablet before I remembered how to make Mathematica do what I wanted to, and I didn't feel like remaking them. Also, this is a better yellow.
Claire, one question from the chat is wondering about how this might relate to the way that the labeling of fractions on the real axis at the boundary of the hyperbolic space, right? Like, so that's a thing for coding continued fractions in the geodesic flow. How similar or different is what you're doing from that?
Who asked that? It is very similar, and it is maybe strictly inferior to doing it that way. So if you are familiar with doing the geodesic flow, that picture will appear. This is half of the fundamental domain. And basically it's dealing with the z-bar is doing that. And I think that this is maybe a somewhat inferior way, but if we're doing,
is it that you're going to unfold this a little bit like you did in the Euclidean case, and then you have something that's more like a traditional geodesic flow cutting sequence?
Yes, exactly. So for those of you who that may make sense to, yes, we're going to unfold this like we did before. and we'll get a cutting sequence. I'm going to call it a bounce sequence, although I think it is truly actually a cutting sequence. But I'm going to call it a bounce sequence because I feel like it.
It's your talk.
Yeah. I will say that this comes from like part 2 of one remark of one paper I read for my candidacy exam. This is like not, the geodesic flow is definitely like, you get so many things for free when you do it that way that it's definitely a better way to do it. But we don't have to talk about left and right while on a Zoom call by not doing it that way. Yeah, so it's something like this is a way of bouncing. Maybe since people have hinted at it, we'll kind of jump a little to the unfolded version. But this is an intentionally very simple pattern. But what we're going to do, and unfolding is going to help this visually, is keep track of how this ball bounces. So say it's coming down from up in this way up high. Right, and so we're going to actually keep track. We're going to call the yellow A, so it hits A, and then it hits B, and then it hits, we're going to call the red C, and then it hits A again, and then it hits B, and then it probably hits A again. Stop drawing it, but it'd be very weird if that bounced down. So this, right, so this is kind of the idea, and certainly we'll tie into the more standard way of doing this, but also similar to what we did when we were tracking the top and the sides of the square. But it can get bad fast, right? Like this is not very, this is already pretty crowded. Right, so this is, we don't really want to work in this tiny little keeping track of how things bounce square. So we are, or it's a triangle, going to unfold it, and reflecting across this yellow and blue should hopefully not be too scary because they are like Euclidean vertical lines. And now Mathematica is going to show it. Right, so this is, ignore the red, that's the dots, that's just my code does weird things. So if you are used to working on like PSL2Z, that's great. Like this is your standard fundamental domain for PSL2Z. And then if you are familiar with kind of the geodesic flow version of continued fractions, some people use that. I prefer the like this version, fundamental domain. So, right, so if you are familiar, there are like hidden in here is the geodesic flow version, but why not play with billiards because we can. So the other thing is if you look at this, just this gray shaded version of the unfolded, you can see this will glue up to be a sphere. I mean, it's like not geometrically, but topologically a sphere. It's a very weird geometry going on. I have pictures somewhere. Oh, maybe not this one, but I have pictures somewhere of some of the things you get. And then, right, and then as Noel said earlier, then it gets scary because now we start reflecting over that red line and then iterating, and then we ask Mathematica to do a little bit of the work for us, and maybe the colors didn't come out as saturated as when I was looking at them in Mathematica, but you get something like this. And they get small fast, and finding those intersection points to switch between red and blue is very annoying, so I stopped drawing them. But you get something like this where you tile, and then again, if you're used to looking at like a tiling of the upper half plane, the red and blue lines are your normal tiling. Just it switches between red and blue, and then the yellow is your fairy tessellation, which is the other way that you typically will see continued fractions come in. which does come up with where all of the rationals on the real line. And so if I had played around with Mathematica for a little longer, I mean, I don't know what size screen everyone's looking at. Like, these might already be too small for a lot of screens. But you start seeing that kind of pattern come up again. But for our purposes, what we really want is that we can like actually draw the full geodesic instead of like bouncing back and forth around this tiny triangle. And now this is what I'm going to call the bounce pattern. Is I put an error, so we've oriented it. So the other thing is, I guess I never answered what is the equivalent of slope, right? Now we have a thing. Maybe this is a good, now we have a picture. What is the equivalent of slope? The equivalent of slope here is actually going to be, let's give things names, alpha. I'm gonna just, so this is easier to read. This is 0. I just realized the font was really small. So this is alpha and this is beta, or whatever names you want to give it. And we're going to find the what alpha and beta are using continued fractions. And then, like, if you think about a line with a given slope, you also have an intercept, right? This is, or some other point on it. This is when we learn how to graph lines. You have a slope and an intercept. And so when we unfolded this, we made a choice as to which line we kept when we were unfolding it, right? And we did this with the square version as well. Like, I picked that upper one, and I picked one with positive slope, just not for any reason, but because it was easy. And then, right, so we also, the other thing we want to pick is we want alpha to be between -1 and 0, and beta to be greater than 1. Because there's no real reason behind why this choice and not any other. It's mostly just to make things consistent.
Wait, I have a question immediately. How, like, you're always going to be able to find an alpha and beta where this is true? Like, you're not going to end up landing between 0 and 1 for beta ever?
Okay, you catch the lie. Okay, or
Sorry.
alpha is the lie. Or alpha is at 0, 1.
Thank you.
I think it is a twofold cover, but yes, I will not lie. How about that? I do think it's a twofold cover, but yeah. I'm questioning in the regular continued fraction case, whether that's in the geodesic flow case, whether that's true. Because I think, yeah, you might need both, but yeah. I'm going to pick this because I'm going to continue to use this exact example. But multiplying by -1 should not be scary, hopefully. So that's all that's going on between the two cases. I'm also not doing any dynamics today, so that hopefully also won't matter that I'm doing anything. I'm just gonna like talk about where the continued fractions come from, not why we would want to do this. So yeah, so you can always get one of these by like picking which arc you fix when you're doing the unfolding. And now we're going to actually get this bounce pattern involved. So what we're going to do is take advantage of the fact that I'm on a touch screen, zoom, so that we can actually see what's going on. So we're going to, again, just keep track of how it crosses this thing, because when it was folded up, this would actually be how it was bouncing. And so I'll write it like next to the points. So there we go. A is this golden yellow thing. B is blue. A, B. Let me zoom out a little. C, B. I don't know why C is on the other side of everything else. B, and we keep going like this, right? So hopefully people can kind of, I'm really just labeling what image or what side we have an image of. And this is why I am calling this a bounce sequence, even though I'm gonna zoom in a second. Even though, like, really, if you want to do all of the actual like proofs and stuff behind it, it does come out to be a cutting sequence. But I'm just keeping track of how it bounces. Okay, so then we have to zoom in because this is kind of close to that point, and we need to see what's going on. CBC, A, B, and we have one more, A. And I mean, there's really infinitely many triangles on either end, probably. With probability 1, alpha and beta are irrational. And yeah, I should maybe say that, is that we do know from the kind of algebra behind what's going on here that the endpoints of all of these lines where they intersect the real axis are rational numbers. We know more than that, but for these purposes, like you're going to have an infinitely many triangles going down as long as everything is irrational. And then I think I should have yes, I made a computer write it so it's more readable here. Right, so we have this sequence, and this is going to actually turn into a continued fraction expansion of alpha and beta, which I will again write.
Claire, you have a tiny gap between your letters. What's that about?
Yes, that's a good call. Mostly it's so it's easier. The string's really long. But that's a good call. I should remember to say that. So because of this rule of how we pick the unfolding, it will always cross the imaginary axis, right? So either you start negative and end positive, or you start positive and end negative. So that's this line. Maybe that yellow is too yellow. And that's where this gap, that's this A. Mostly though, this is because it's a really long thing, even with this like not drawing that many triangles, and it becomes hard to read.
Thank you. Another question from the chat is, does having a rational number for alpha or beta correspond to getting stuck exactly in a corner?
Yes, that is a good question. I'm going to guess that's also from someone who's maybe used to thinking about geometry. Yes, having a rational endpoint is exactly bouncing into these corners. So and I very intentionally in the square case did pick a point that would not hit a corner when I was doing that bounce pass. And we call that like pockets of your billiard table. We really lean into this analogy. And so yes, if it goes down, if you have a rational endpoint, it will, so say you have, like this was your alpha, then that's like it bounces down into that corner. Definitely. So if you had, nope, that's not a circle. That was really not a circle. Okay. So like you had like that. Then yeah, that would correspond to bouncing and getting stuck down in like the pocket or the, it's a cusp if you actually glue it up. Getting stuck in the cusp. Yes. So that's good intuition as to what's going on. Other questions about that? Good. Okay. Yeah. So you may have noticed this, especially when I zoomed in, but there's not the like most stable to perturbations, which I would say is maybe a flaw in the billiard idea. But so we actually do have to do a little bit of group theory here and reduce our word. So what's going on pictorially? So all three of these, I promise, even though it doesn't quite look like this, they really do have the same endpoint. Which means they should all have this, right? Alpha, if it's the same alpha, should have the same value. So we need to deal with two things. We need to deal with this. Maybe yellow is not the right color. Red. Purple. We need to deal with this, and we need to deal with this. Right? Where the bounce sequence is different, but we're approximating, we're getting the same value. And this is where we have a reminder as to what actually is going on algebraically. So reminder is that, like, this blue is 1 minus z bar. Is you actually, if you hit that blue, you're being reflected by 1 minus z bar before we did the unfolding. Red is 1 over z bar, and I'll call it yellow. I don't know what color that is minus z bar. And so if we have, let's see, B, C, B is blue, red, blue. This is minus, or 1 minus 1 over 1 minus z bar. And then this other one, which is red, blue, red, is 1 over 1 minus 1 over z bar. And these are both z bar over z bar minus 1. So algebraically, they're the same. So we can replace one with the other because algebra is going to actually be both. That's why this stuff works. And we are going to actually prefer this one because it makes it work. I'll show in a second why. And then the other circle, actually I have 2 examples for that one. Bring this with us. Right, is this, maybe this other one is a little bit easier to see what's going on, but we also have this AC and CA. And that one is maybe a little bit easier to just see that immediately that's minus 1 over z bar. All right, and so we are going to prefer AC. And then together, when you kind of combine those 2 rules, you get that BCB A, yeah, you get like kind of how to reduce all 3 of these to have the same one. Right? Switching this together. We can do it. You can do it in 2 steps. So this is the kind of group theory of like we want one representation of this endpoint.
So Claire, a question from the chat. Are you saying that 2 paths are equivalent if they have the same alpha?
Yes. Kind of. So you want to, I mean, the ultimate goal is to find the continued fraction expansion of alpha and beta. These probably won't line up anyway, but you also want that on either side of this dividing line. You want the sequence to actually give the same value, and this just kind of permeates through the equivalence class. I don't know if that makes sense. of like, basically like where I put that space, we're dividing it and saying, this is the part that divides to alpha, this is the part that is equivalent to beta. And then once you've kind of done that split, they should all algebraically agree. And this kind of gets you to one unique representation of that path. And that, I don't know, did that help explain it?
Can I just ask, did the dividing line was based on what we chose to be the fundamental domain? Was that it? Okay.
Yes, the dividing line is based on the fundamental domain, or yeah. It's a I don't know if saying it's a section of the geodesic flow necessarily makes sense when we're talking about billiards, but it's an analogy. It's our decimal point in the sequence. Is the other way I like to think about it. Is like we have this sequence that goes off in both directions. This is just kind of dividing before the decimal point from after the decimal point in the symbolic. And then if we go back to the example here, well, we have, I'm going to highlight this because at least to me, I find that helpful. We have this, right? This BC, well, let's do it in 2 steps. Right, so we said BCB, we replace, and CA, we replace. But I'll do this in 2 steps, right? So ABA, no problem. And then we take it with CBC, A, and then BA, BA, C, BA, C, BA, and then this one we also need to switch, right? I will do by this because I assume that no one's actually taking notes. So it's okay to do bad things like that. All right. And like I said, this kind of is our dividing line between the part that corresponds to alpha and the part that corresponds to beta. And I think I have it typed where I maybe have a little bit more room to write, and it's a little bit easier to read, not my handwriting. So what is going on algebraically here is probably like the thing that we need to address, right? Because otherwise this is just a picture with not a whole lot, like it's pretty, but like it's kind of coincidence of it if we don't justify this. And the thing to note is B, I think I kept using capitals, so we'll do that. BA to the n is n plus z. So CBA to the n is 1 over n plus z. And this is starting to look like actually getting a continued fraction. Like as you travel along this path, you do all of these things and you kind of concatenate them to get a continued fraction, which is why I made the decision to put the C where I did. So
Claire, yeah. A question from the chat is about like, when you start doing these replacements that come from the group theory and the way these compose, and you use those relations, you end up with lots of BACs. But like as that question came in, you started grouping them as lots of BAs. So can you clarify which is going to be the important thing to really stare at?
So C is kind of like, so okay, so we're doing dealing with the B and C so that everything looks like this form, CBA, BA, BA, instead of having something that has a like CB and then just no A there, or CA. So it's just to kind of get it to, so that every single thing looks like this.
Where by this you mean groups of BA
Groups of BA,
with C's
yeah.
in between them.
Yes, and then the C's are going to tell us next fraction.
Okay, thank you.
Which is, yeah, the next thing I was going to say is how to read this. And maybe again, let's make some of the font a little bit bigger. That's 2, 3. And I'm actually going to deal with beta because the intuition's a little better first. So here, right, this is 2. Should go between 2 and 3. That's good. Plus 1 over, and then this one's going to be a 1, plus 1 over, well, we don't know because I stopped drawing triangles. So we'll do a dot, dot, dot. And this is 2 plus a half. So maybe some intuition as to why this makes sense. So it's between 2 plus a half and 3, which means we want to divide by something less than 2, right? Because that will make the entire fraction bigger by dividing by something smaller. 1 plus something is going to be smaller than 2. So that's kind of the intuition that this is at least somewhat a reasonable thing to be doing. This is where it ties in very well to the geodesic flow question, where this is truly analogous at this point to what you do there. And then how do we handle this other endpoint? All right, this is our 0. I mean, the real answer is you hit it with -1 over z and you turn it into this endpoint. But the other way you could do this is read this like backwards. So we read this as like the first chunk. And then, all right, sorry. Yeah, but it's like there's a C over here. Is like our chunk, or the way I like to do it is you just write it in the other order, right? So you just write CA, B, and then you, wait. So we hit it with -1 over z, which is AC, which makes these cancel, right? And you can write it that way. But the maybe scarier way to do this is to say, okay, this is 1 over 1 plus something. There's a C, say there's a C right here. This is 1 over 2 plus, maybe it's a little scary to say we read this direction. But I promise it works. And you keep going that way. And then we know, because we chose this is between -1 and 0, we know it's negative. That's morphema. We declared it to be negative. And in the other case, right, we would have put the minus up front because we knew it was negative. That's just from the choice we made. I think I just have more copies of this to keep drawing on it. For some reason, I was like put in multiple copies of this. I think this is, yeah, not going into the like dynamics of this, but you can get dynamics to behave properly out of projection maps if you are the kind of person like me who actually that's why you're doing this. The other reason I will say, again, this is maybe not quite the best way of doing it, but you can get orbits of group actions on the upper half plane, like classifications of orbits, which is a reason that geometers like this. And so going back to when I first put up the picture of the upper half plane, someone said, is this going to come back to where it returned? Can it come back to where it started? Which is a really good question. And this, I think, is maybe a good way of seeing how that happens, which is that you have to have a periodic, well, you have to have a periodic path. That's right. It has to come back to where it started. But that means that the bounce sequence will also repeat in, forever. So if you have just this, it does have to be purely repeating. So you have one chunk that repeats indefinitely in both directions. That is going to be the balls that come back to where they started. This happens to be a classification of roots of quadratic equations, which geometry is not the way to show that. So I will just state that that is the case, that this is, they will actually be, if that happens, your endpoints will be two roots of the same quadratic equation with very specific continued fraction expansion that is also periodic, with the one forward and one backwards.
I have another question from chat for you.
Yeah.
So if you start with a continued fraction for some number alpha, can you find a bounce sequence that is that continued fraction without needing your replacement scheme stuff?
Yes, you can do that. This is bijective. Bijective? It might be 2 to 1. But yes, you can. If you have the continued fraction expansion, often when I'm making these pictures, that is how I decide what I'm doing, because if I start with the continued fraction expansion, I can like tell how quickly the triangles are going to get really tiny, or like if it's going to blow off screen in a way that's going to make me have to like zoom out really far. So yes, it's actually really helpful that way. You might need to choose your alpha and beta independently, because you do need to make sure to not do the reduction. You need to make sure that you go above -1 plus I root 3 over 2. Because that's going to be the point that determines whether you have to do these reductions. But yeah, you can do it. You can, as long as you only care about that one part of the sequence, you should be fine. Other questions? I don't normally talk about billiards, so.
Does going up above that point relate to the, like what I was asking about before, about seeing where alpha and beta have to land? Like when you really want to,
that seems right.
like you've got to be so far apart to like stretch up above the point?
Yes.
Okay.
So what you really, trying to think. Yeah, I'm trying to think. So you definitely are going to pass. Are you going to definitely have, you may know. Yeah, it should be related to like which like unfolding you're picking. Like I said, it's not quite, I normally do the full geodesic flow and not the billiards. I would say maybe the reduction is, and this weird justifying reading backwards, although you have to do that in both cases, but the reduction is maybe one of the other arguments for why this is not standard way of doing things. Also that it came like 30 years after the one that gives you more results. Right, like I said, this is a remark in a paper that's like doing not normal continued fractions. And because of that, in that case, like the actual case the paper is considering, it made a lot of sense.
Okay.
This case, yeah, I thought I had some fun to figure out some billiards. Other questions?
Okay, Claire. So you've been these functions are transformations.
Yes.
And then you're using the function, and you're describing from the function what the value is, right? Is alpha, and there's lots of points inside the original billiard triangle that would have been on the same geodesic. So it's not like you're plugging one number into this function and getting an output.
Yeah.
Can you
So
say more about that relationship?
yes, I can. So I would say the first thing is that the functions are maybe a justification for why this works. But okay, so what is actually going on here? Is really what you are doing is you need to act by something that shifts you from one case to another. If you like, and that's really where so really truly what you're doing is saying like, okay, so we cross between the imaginary axis and 2. Your balance sequence is always going to be BA, BA. And then we act on this entire geodesic by subtracting 2, which is going to be the inverse of that, right? It's ABAB. And that takes us to a new geodesic that lands between, oh, I haven't actually done this out. That might land between 1 and 2 and not between -1 and -2. Because that bounce might be doing something funky there. Right, so really you're acting on these endpoints and you're actually truly finding like one thing, doing a function, finding the next one, doing a function. This is like a shorthand for doing all of that. And instead of saying there's matrices hiding everywhere, I'm kind of secretly maybe hiding them slightly less than I normally do, which is I at least wrote down a function, not matrix. Oh my, I don't even do that. So yeah, what you're really doing is finding like the first digit, act on it, throw it out, find the next digit, act on it, throw it out. And that corresponds to how, like, from the symbolic dynamics world, we actually do continued fractions. It's just, again, the Euclidean algorithm is easier than doing that. Other stuff, I think we actually are managing to be close to on time.
Any last questions, Noelle?
You're all only free trade friend.
But like, I see there are more slides and I'm wondering if there are things on them.
There's this, and then there's blank pages.
Okay, all right.
It's because I'm in a note-taking app,
That makes
so that
sense.
I could draw on it. I thought maybe this one would be too cluttered, and I'd want a fresh version. There's not much anything there.
Was it?
Well, thank you for asking that, Noelle, because I was waiting for the last slide to say,
Oh.
let's take the speaker. So
No.
let's take
One
the
more.
speaker, first of all.
I have one more question from the chat that I think you can handle. Is there anything special about a line that starts vertical?
Oh, like if we were to start our bounce that way? I think
I believe that's the question, yeah. So
Yeah.
suppose the curve you're studying is a vertical line.
Right. See, now we have a nice thing we can draw on. So, I mean, it wouldn't fall into our case, but I guess I mean, no one's ever asked for that. I guess you could figure out how to like find this, and then this is infinity. My naive thing to do would be to hit this with -1/z. Right, because then infinity goes to 0, and whatever this goes to. And I think the -1/z is my bias towards PSL2Z instead of this weird thing that has -1. But so I think you could do it. It's certainly not the standard way of doing it. But we know the top isn't bending. So it should work fine.
All right. Well, thanks everybody for coming and hanging out. It's 15 after the hour, so we're going to go ahead and cut the recording at